All right, kids, let's have fun. So today's big picture day. So we're moving into chapter 4. Toot sweet as we go here. Chapter 4, of course, is applications, you see, of derivatives. Oh, you dumbass. Applications of derivatives. Wait, Groom, haven't you taught us some of this already? Listen, bro. Shh, don't tell anyone. The way I like to do this thing, it just makes sense, okay? I can't tell you, hey, we're going to have fun doing this. Won't that be fun? We just did it. Well, why am I doing it? Well, listen, a good teacher tells you, at least whenever possible, why we're doing what we're doing, for crying out loud. So, you've already told us what first derivatives mean. Yeah, I know. So, like, that's what we're going to use them for. Some of that, yeah. And then we're also going to talk about, well, what are we going to do with that? And then it's going to be pretty sweet. So several things. So first of all, we're going to talk about optimization. You see, not we actually need that's optimal. That is optimal. Well, how do you know it's the best? Wait, is it the maximum? Well, listen, pal. Do you want to spend the most money you can? Well, it turns out you can't do that. Ha! Do you want to spend the least amount? Yes. Ooh, we can minimize certain things. Nice. We can maximize our weight loss. Nice. We can do all kinds of crap like this. We can maximize our, wait for it, a profits. That's right. And so when we do these things, for instance, let's say you want to maximize profit. Of course, we're going to talk, we're actually going to have to do some business. How exciting is this? Profit, of course, is what? But there's no E in profit, moron. Don't mind me. Is equal to revenue. How much money's coming in minus expenses. Nice. Nice. And so what's kind of cool about this is that when you do this problem, this is going to be profit is going to be some function of X, how many things you're making. That means revenue also is, and that means expenses also is. Nice. And so when we start looking at these things, like, oh, sweet. I'm just going to take profit like so. That's right. And set it equal to 0. That's right. That's cool. But wait, Groom, wouldn't that be the same thing as taking that derivative minus this derivative? Set it equal to 0? That's right. Wouldn't that be the same as saying that this guy is equal to this guy? Don't say yes yet. Yes, that's right, Groom. Whoa. 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 Okay, so some cool things. This is the profit. This P prime of X is the rate of change of profit if I make another thing. You with me? If I make another widget, as the kids say. Let's make another widget. I've already made 1,000. Let's make another one. Cool. What happens to my profit now? Does it go up? Does it go down? I don't know. I don't know. But here's what I do know. This is the revenue if I make one more item. This is referred to as marginal revenue. This is what's known as marginal expenses. Wait, at some point they'll be equal. That's correct, friends. If at any point you cease gaining revenue, and so the rate of change of revenue becomes equal to the rate of change of expenses, then you should stop making more stuff. You with me? Because if I made more, it's going to cost more, and I'm going to then be getting less profit. Some people will be like, bro, you can always make more. Well, bro, what if I'm already working 3 shifts of people? Well, add a 4th shift. Bro, there's no time in the day for a 4th shift, for crying out loud, you freaking goof. Well, add 3 or 4 more. Okay, dude, we're completely full. I know, we'll build a new place. Well, that's not cheap, bro. If I make one more thing, I have to build an entire new building, spend $1 billion and all that. I don't think I'm going to do that. That's just silly. You see that? That's goof. So we're not going to do that. That's just that idea that, hey, at some point it doesn't make any more sense. You can keep making more stuff. Yeah, our revenue is going up, but our expenses are going up faster. Wait, that means our profit is then coming down. Again, P of X, this guy right here, for you, I really hope that whatever you're selling, it looks something like, whoa. And somewhere right in here, if you make that many things, you will maximize profit. So actually spending quite a bit of time talking about some concepts, business concepts, actually, in this class. It's kind of fun. So that'll be a good deal. Yay. Oh, wait, stop, come back. So clearly we had positive slopes. We had negative slopes. Somewhere in the middle, as long as we have a continuous function, we must have a zero slope. And you see we went from positive slopes to 0 to negative. This is what's, so this is a maximum always. And if we went negative, 0, positive, this is a min. This is what's referred to as the first derivative test. If you have a critical point, remember a critical point is where the first derivative equals 0. If you have a critical value, and on the left side of it, it was positive first derivative. On the other side, on the right side, it's negative first derivative. Then you have that critical value is a maximum. Okay, so we'll talk more about that. We've already mentioned that. We will actually codify it, and we will say, hey, listen, that's the first derivative test. Well, that's pretty cool. That's kind of a neato thing. So we're doing quite a bit of that. Along with that idea that extrema, we'll also refer to these as extrema. You mean maxes and mins, Groom? Yes, that's what extrema means, crackhead. Exactly. Along with that, of course, we'll be like, whoa, that looks like a point of inflection. I agree. And so we've talked about that when it comes to second derivatives. We're going to use them a little bit more. Of course, this is concave down. What does that mean? It means f double prime is less than 0. And over here, f double prime is greater than 0 because we are concave up. Yep. Nice. And that's cool. Listen, here's a question for you. Suppose you had a critical value. So that is f prime of x equals 0 here, yes? But f double prime of x is negative. What does that say? It tells me that this must be like this. That means that's a maxima. This is what's referred to as the second derivative test for extrema. Okay? So in other words, if you have a critical value, which means you already have the first derivative, I mean, duh. And then if you take the second derivative and it comes out to be negative, that means it's concave down. Ergo, you're looking at a maximum, or if it's concave up, then of course it's minimum. Okay? Piece of cake. Now, like what else cool things we do, Groom? Will we actually talk about our graphs this way? Yeah, I've already told you this. So as we're moving into this, we've already looked at shapes of graphs. Is it concave up? Is it concave down? Things like this. We'll also talk a little bit about this. I will say that f of x is increasing on 2, 4. Okay, cool. 1, 2, 3, 4, bitchin'. All right, boom, boom, boom. Whee! There you go. I don't know what happens at 4. Oh, wait, yeah, I do. F prime of x is equal to 0 at x equal 4. What? Nice. Wait, f of x is increasing x greater than 4. Wait, so it did this and then took off again? Apparently. Okay? Apparently. Wait, then Groom, what was happening over here? I don't know. I haven't told you yet. So f prime of x, f prime of 2 rather. F prime of 2 is 0, and then f prime of x is greater than 0, x less than 2. Bloop. Hey, minimum, yay. Is this a max or a min here? It's neither, actually. It's a plateau. We don't call it that, but yeah, it'd be a plateau. And notice it's concave down, and now it's concave up, right? So like right there, what would you have? F double prime of x would be equal to 0 right there. Okay, point of inflection, of course. There's probably going to be one right in there somewhere too, yeah? Has to be kind of, you know what I mean? It kind of has to be, bro. Okay, so we're doing some talks about that, some sketching of graphs, describing the shapes of the graphs, all that good stuff. Okay. Now, what if I told you that a function was monotone? You mean the opposite of group? That's right. A function that has no passion. A function that has no depth. A function that has no excitement to it. So what we'd say is this: we could talk about this, something that has a monotone increasing function. Okay. Okay, it is constantly increasing. You with me? It's monotonous, if you will. Okay, it's doing the same thing all the time, if you will. Okay. Oh, I'm gonna die. I feel like it is summertime, and I've been out in the grass tonight, which I have not been. That's what it feels like. Okay. If I can find my notes here. One moment, please. 1 moment, please. Nice. Right. So there it is. So it's monotone on. Now, the way I've drawn this is it's increasing on the entire interval. Okay, we call that about monoticity of the function. Okay. Yeah. Now it can be monotone, increasing or decreasing on a particular interval. The function itself doesn't always have to be increasing. For instance, when x is bigger than 0 here, it's a monotone increasing function. And I suppose you'd say on the other side, monotone decreasing function, of course. Okay, good times, wonderful. We'll also be talking about asymptotes in this section some more. Like, gee, we already know asymptotes, Kroom. Bro, I got you. Wait, but asymptotes have to deal with typically what happens as we go to infinity. You're right, of course. Wait, doesn't that typically do things like this, fella? Well, of course. So what is the limit of this function as x approaches infinity? Well, of course, it's 0. What does that mean? It means it's doing this number. Woo, yep, heading towards 0. Nice. And so we'll look at those guys. We'll talk about asymptotes. We've already talked about horizontal, or let's say you had 2x minus 1 over 2x plus 1. Yay, this will approach 1 over time, right? And so over here, it's going to be like approaching from the bottom side, I believe, something along those lines. Okay, don't quote me on what's happening over here, don't really care. But it's approaching this from the bottom side. On this side, it's going to be approaching from the top side. How exciting. And we're going to talk about these things, okay? And so we're going to spend some more time with them. We're also going to say, like, hey, what happens to this function, the ln of x, as x approaches infinity? Well, we already know that it's headed towards there. This function is monotone increasing, okay? But it's headed towards infinity, right? It doesn't have an asymptote. It's unbounded. It's going to continue going up. Some functions, like this guy, the limit as x goes to infinity is really just 3x squared over 2x, which is just 3x over 2. And this fellow, we would say, is approaching this line. Yeah, some kind of situation, a slant asymptote, perhaps. And we'll talk more about that. Now, one thing we ran into issues with in chapter 2, and we just kind of went, well, we just waved our hands at it. And we said this: if you want to take the limit as x approaches infinitas of 5x minus 1 over 2x squared plus 2, hey, Mr. Groom said divide by x squared. He did say that, because that's the highest power of x in the denominator. And so now you end up with 5 over x minus 1 over x squared. X, that's just 2, that's just 2, plus 2 over x squared. Take the limit as x goes to infinitas, and you end up with a big fat 0 on top over 2, which is 0. And we talked about that, but we are going to find a way to actually compute this. Okay, because what we did there was fine, of course, but there is a better way of going about it. Okay, and so we're going to see that. We're going to see that and use that. So the idea is, and I mentioned this when we were talking about these before, who is winning the race to infinity, the bottom or the top? Well, it's the bottom, of course, right? And so what we're going to find out is that there's a rule. It's my boy L'Hopital. Yeah, L'Hopital. Or something along those lines. Anyway, L'Hopital said, hey, listen, if you have infinitas over infinitas, plus or minus, doesn't matter, or 0 over 0, bro, this is problematic. But Mr. Groom, my Mrs. So-and-so told me that 0 divided by anything is 0. Well, she was a liar because everything except 0, that's true for, bro. Wait, you mean it could be something else? Yeah. Mm-hmm. And infinity divided by infinity should be 1. Oh, you sad, sorry little... Oh, that's terrible. So what we're going to see is these are what are referred to as indeterminate forms. If you have such an animal, then what you need to do is look at it this way. So if you have one of those, and you're trying to take the limit of f of x over g of x as x approaches anything, okay, and this ends up being this over this or this over this. If that's true, then instead what we're going to do is we're going to take the limit as x approaches c of f prime of x over g prime of x. The idea is that we can't have 0 in the basement. We can't have infinity over infinity. So if we were to get, for instance, 2 over infinity, well, now, hey, that's going to 0. If we were to get infinity over 2, that's going to infinity. If we were to get 0 over 2, that's going to 0. You see what I'm saying? If we did this and we got 2 over 5, then the answer is 2 over 5. So we're going to do a bunch of these later on, but the one I want to do tonight for fun is take the limit as x approaches 0. And we already know the answer is 1. We gave that by definition. But look what happens when you put 0 in. You get 0 over 0. Oh, no. That's the indeterminate form. It is. So what are we going to do? We're going to take the limit as x approaches 0 of the cosine of x over 1. That is the limit of the derivative sign, which is cosine. And the limit is the derivative of x, which of course is 1. And you take the derivative of this, you plug 0 in, you get now, well, the cosine of 0 is 1. 1 over 1 is 1. Yay! That is L'Hopital's rule. Okay? And some, here's another one that we'll see later on, the limit as x approaches infinita of 2x minus 1 over x squared plus 3. So if I take the derivative of that, I'm going to get 2 over 2x. Damn it, 2 over 2x. What is the limit as x approaches infinity now? 0. Yay. But wait, what if it was x squared and x cubed? Bro, that would be 4x squared on top over 3x squared on the bottom. Oops, sorry, 4x on top. Groom, if I put in infinity, it's still infinity over infinity. Oh, no. Oh, no. Well, let's do it again. Now what is the limit as x approaches infinity? Well, it is 4 over infinity, which is approaching 0, yes? Yay. And the idea with that is this. If we are, when you took the first derivative and it was still the same, what that means is they were approaching at relatively the same rate. So then I need to go look at their accelerations, okay? I need to go look at their okay, yeah, they might be traveling at the same speed now, but who's accelerating faster? Okay, on the way to infinity, as it were. And that will tell me then, okay, oh, I see, and so on and so on and so forth. Yes, it works for the 15th derivatives as well, if that's what you need to do to get something other than infinity over 0 over 0. Again, that only works, Hayden Moore, that only works is if it's 0 over 0 or infinita over infinita. But, Groom, I got 5 over 2. Then your answer's 5 over 2, you goofball. Jiminy Christmas. Okay? Now, a couple other ones that we will do in this section, which I think is kind of fun, is, well, I think which do I want to do first? Yeah, I want to do this. So if I have some random function doing its thing, yay. And here is x equals 1, 2, 3, right there. Nice. So this is 3 comma f of 3, if you will. Let's say that you would like to know what is f of 3.1 approximately equal to. And you're like, Groom, I don't know. I mean, like if I knew what F was, I could just plug it in. Bro, you could. But remember in the old days, we didn't have a lot of calculators. And it was hard. That's before my time, by the way, pal. I'm not that damn old. But anyway, before that, my time, they didn't have a lot of calculators, and they needed to have a way that they could simplify things. Additionally, for programming, this works out well. Okay, for computer programming. Additionally, it proves a couple other points to us later on. So what I want to see is this. What would be really cool is if, oh shoot, it'd be really cool is if I could find the equation of a tangent line. Oh yeah, dude, that's hot. I can do that. Y equals mx plus b. I agree. You're not wrong. Oh, by the way, this is, I'm going to write this f of x is approximately equal to, because my actual function and my line are very similar, yes? F prime of x times x minus a, so in our case x minus 3, plus f of a. Okay? So I'll try to pinpoint that so you can see it. Remember that you can always start off with m equals, yes? X2 minus x1 over, you dumbass. Y2 minus y1 over x2 minus x1. And so if I just pretend these are my x's and y's here, my original x's and y's, the ones I want to keep in the equation, then what I end up with is y minus y1 equal m x minus x1. Okay? Now, which is which? Well, this is some value a. This is some f of a. You with me? And so this is y minus f of a is equal to, now this fella is who? Well, that's f prime of x. F prime of x times x minus a, and then plus f of a. And so what we end up with is what we're saying is that your equation is approximately, the actual equation is approximately what this line is. Okay? So let's just pull one up here in the old Desmos machine, have a look-see here real quick. Okay. May your Christmases be white. I am dreaming of a white Christmas, just like the ones I used to know. Oh, that's hot. No, I can't use that. No, that's terrible. No, I can't use that because everyone will get all mad at me. Oh, Mr. Groom, that's a hard problem. You're so mean. You're a horrible human, Groom. I know. I've been told. Why is this cube? Get rid of that thing. That's stupid. Oh, I know. Oh, that's hot. Yes. Oh, yes. Where's it at 3? Oh, that's embarrassing. Oh, no, there it is. Bam. Look, friends, at 3 we are at, I don't know where we're at. We were figuring that out. X equal. Boom. Ugh. Now listen, that function is clearly curved. You with me? It's not as curved as some functions on this planet, but it's a little curved right there. You're like, Groom, what if it was x squared? Glad you asked. Let's try squared. You just want to curve it more? I do. I just want to curve it a little more, you see? So now I have 3 comma 9. Dude, I love it. What if it was just positive x? Let's just do this guy. Oh, that's mucho better, senor. Mucho better. Ching. Oh, let's do a +1 on the end just for a good time. +1, +1, +1. Nice. Now, Grim, what are you saying? Well, what I'm saying, sir, is that I can create an equation. So what I have, x squared. So if I have x squared minus 3 root 12 minus x. 3 root 12 minus x plus 1. That's my f of x. And I would like to know, hey, what is f of 3.1, for instance? Okay. Well, here's what I want to know. Okay. I already know that 3 comma 1 is a point on the graph. Yes? 9 minus 9 plus, yep, there it is. Okay. So I know that my line that I'm going to be making here, my line is going to be equal to the slope. So I need to find my slope, so I'll wait for that for a minute. So it's f prime of x. I haven't done it yet, but just hold tight. And technically it's f prime at a, by the way. You with me? So f prime at a times x minus a plus f of a. Okay? And so when we do this, again, just kind of keep this in mind. We've already done it, but we're going to actually start applying it. You with me? So this is 3x minus 3, I should say. Okay? X minus 3 plus f of a, which f of 3 is 1. So that's hot. Nice. And then the question, of course, then is, well, what's the derivative here? I haven't found, f of x. I haven't found the derivative yet. So the derivative, of course, is going to be 2. And then this is, remember, 12 minus x to the 1 half. So it's going to be minus 3 halves. 12 minus x to the minus half times negative 1. So it's going to be that thing. And so then what happens at 3? Okay, well, what happens at 3 is, if I plugged 3 into that guy, I'm going to get 12 minus 3 is 9. The square root of that is 3, and it's negative, so it's going to be 1/3. So this is going to end up, the 3 is going to, so you need 2.5. So my slope's going to be 2.5. So if I graph that, what I should see is that's a tangent line. So 2.5 parentheses x minus 3. Oops. Oh, shh. Plus 1. Do. Okay, so that means Mr. Groom messed up. What did he do wrong? This time. Oh, it's 2x, you jackass. That's what you did wrong. So it's 6 plus a half is 6.5. Atta kid. I bet it works now, moron. Boy, you're dumb. Hey, look at that green line. Looks just like the red line. Bro, they're indistinguishable almost. Let's don't get carried away, pal. But yeah, they're indistinguishable. Pretty close. But wait, what are you saying? Are you saying that if you just put 3.1 into here, you're going to get an approximation for it? That's what I'm trying to say, bro, but you're not listening to me. 6.5, 3.1 minus 3 plus 1. Well, this is 0.1. Are you with me? That's 10%. So this is going to be 0.65. So it's going to be 1.65. Ta-da! Groom, what if I put 3.1 into the original function? Can I do it? Well, with a calculator, obviously. Okay, let's ask Betsy. Oh, Betsy, 3.1 square. It's 31, jackass. 3.1 square minus 3 squirt 12 minus 3.1 plus 1 is, give it to me, 1.66. Dog, that's pretty close. All right? Now, clearly, the more curved my functions are, wait a minute. Won't that have to do with second derivative, Groom? How curved they are? Dude, you are sharp. Bro, you're right. The more curved they are, we cannot go out as far from our particular a value. Okay? So if you had a function that was as crooked as a dog's hind leg, and you wanted to predict, like right in here, okay, well, near x equals a, what is that crappy rendering there, bud? Near x equals a, like really close to it. It kind of is pretty close. But let's say I want to go over here to here. Bro, they're not even close. What are you doing, bro? What are you doing? And so something else that we'll look at, but it won't be till later, is we will actually talk briefly this this year about what are called Taylor polynomials, or well, Taylor's the Maclaurin series, and polynomial is a different one. But anyway, the Taylor polynomial is, instead of creating a line to mimic a curve, I can create a polynomial to mimic a curve. And what they'll have is they'll have a point in common, check. They'll have a first derivative in common, that's cool. They'll also have the same second derivative, third, fourth, fifth derivatives. The idea being, when you do that, they should really match each other if they share all those things in common. Okay, so that's pretty cool. It's a lot of fun. Something we'll also talk about right here. This is referred to oftentimes as delta x. It's the change in x. In our case, we had a change in x of 0.1. Okay. By the way, another way to write this problem is delta y is approximately f prime of a delta x. Okay. What do I mean by that? What I mean by that is this. Okay. If I want to know, maybe I don't care how many total people I have at a certain time, but I want to know how many more people I'm going to end up with. You with me? Like, okay, well, you're doing what now? Oh my word! I'm going to end up with 20 more people or 100 more. Oh, I'm looking for this. So when I change my x by, let's say I'm going to do something else, I'm going to lower the ticket price by $5. Bro, you're telling me I'm going to get 100 more people. That's correct. And so again, this is simply y2 minus y1, right, is equal to, this is just where this comes from. It's just a different way of looking at it. We'll spend some time with that this chapter as well. It's a good time. Good time. Good time. And then the last thing that we will do is we'll talk about the so-called mean value theorem. So let's say I drew this picture, I think, before. Oops. I haven't drawn this picture for you before. Here we are leaving the house. Oh, did you get the bag? No. Did you get this? No. Ah, crap. My curling iron. Oh, no. Pew! Okay. Again, this is the one I like to use. Here it is. We took 5 hours to get to my parents' house. It's 300 miles. Nice. That means our average speed was 60 miles an hour. Right? As if we'd done this. Correct? The mean value theorem talks about how I know that this is a continuous function. There's at least one time where I was doing 60 miles an hour. And according to the picture, it's pretty obvious. I did it right. I was doing it right here, right? Right here, right here, right here. Because at those points, there's obviously more. Don't be ridiculous, of course. Oops, and right there. Ooh, 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 ooh. All those places where they're parallel, I was doing 60 miles an hour. Are you with me? Because we had the same what? Same rate of change or the same slope, right? And so we know it had to happen at least once on that interval. Okay? And so that is a fact. Okay? Oh, you drove 200 miles. You did it in 6 hours. Well, that's in 5 hours. Dude, it's 40 miles an hour on average. But I did it all in 1 hour. I was just, sat at McDonald's the rest of the time. That's disgusting. That's weird. But I guarantee you that on your hauling butt part of the trip, even if you're just going from 0 to 150, you had to have hit what? You had to have hit 40 somewhere in the middle there. Okay? And it's pretty easy function. Like, how do I do it? Like, I take f prime of x, set it equal to that value. Set equal to that value. Where does that equal that value? So let's say that this was f prime of x. When does it equal 60 miles an hour? Are you with me? And then I just solve this. Remember, this is an equation. I don't know, x squared minus 6x, or whatever this function is. I don't care, really, right? Minus 60 in this case is equal to 0. And you solve it. See that? And don't make up the x squared minus x. It's just a particular function, right? But does that make sense? You just have a function set equal to a particular value, say 60, and then solve. This is where it happened. Boom, 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 boom. This is where that would have occurred and taken place. It's called mean value theorem. It's pretty straightforward. So these are the topics that we're going to be doing in chapter 4. It's really straightforward. You'll enjoy it. If you don't, I don't have to tell you, you're a sad, sad individual. You're a sad individual. All right, I'm going to shut this off.